My name is Alex Bray, and this is Lab 11, Motion of a Swing. The objective of this lab was to model the motion of a swing and extract velocity, momentum, stretch of the rope, and the components of the forces acting upon the mass. The result was the velocity and momentum peaked when the object is in motion and not when it's at its momentarily stationary positions where it peaks in the y direction. The rope encounters the biggest stretch and tension when the mass is at its lowest y position. The parallel net force is relative to gravity, and the perpendicular net force is related to the spring. So here's my video, and I used the person's height, which he was standing earlier in the video, as the calibration stick, and it was about 1.8 meters. And here's the code that I made for it. It updates velocity, position, momentum, stretch, and the forces all down here. And then I inputted the person's mass, 68 kilograms, his starting position, which was extracted from the tracker data. I found the spring stiffness and the unstretched length of the spring. So here's a run of the module. The black arrow is the total net force, the red arrow is the perpendicular net force, and the blue arrow is the parallel net force. The velocity, here are two graphs of the velocity. The red is the model's position, the green is the tracker video's position, the blue is the velocity. For the y-coordinates, when the ball reached its maximum positions in the y direction, the velocity approached 0. Depending on the direction of the ball, the velocity increased or decreased when the ball was in motion. For the x-coordinates, the same application was true as in the y-coordinates. For momentum, the momentum is also in blue. The momentum fluctuates a lot more since the mass is 68 kilograms, which is somewhat heavy. Compared to the velocity because of the mass. There's a great momentum even though there's small velocity. So even though velocity is small, the momentum, the mass is very great, which makes the momentum great. For the stretch is in blue. For the y-coordinates, the stretch of the spring has more to do with the y-coordinate system than the x. As the ball approaches its lowest point, furthest from the origin of the spring, the stretch is the greatest because the spring is encountering the greatest resistance due to the force of gravity on the momentum. The spring's force is trying to counter that of gravity, and thus must stretch some to help with the counter force. And if you see by this these formulas, the gravity is becoming greater with a lower y, and so the force of the spring must equal the force of gravity, and the force of the spring must also become greater, thus increasing the stretch. So as y gets smaller, the force of gravity increases, thus increasing the counter spring force. For the components of force, red is the net force, green is the parallel force, and blue is the perpendicular force. The parallel force increases when the ball is at its peak y positions because the force of gravity is trying to pull the ball back down. The perpendicular force increases when the ball is at its lowest y position because the spring is trying to pull the ball back up. So the parallel force is related to the force of gravity, and the perpendicular force is related to the force of the spring. Drag force. What if drag force is taken into account into the model's prediction of motion? The motion will not change enough to be noticeable. The force of the drag is too small to be recognized due to the small speed and the non-air resistant makeup of the body. But here is a code to simulate drag force, and the drag constant I found to be 0.05, and I used this formula to include drag, and it is also included in the net force. So after a run of this module, you can easily tell that there's basically no noticeable change in the motion or in the graphs.